Okay, I think it's time to start. Thank you all for being here. Thanks, Professor Kalogeiton, for being here and making this nice presentation, because it's actually very interesting what we have here. We're going about visual generative AI, and particularly on the scale of all this context, which is so important in not just computer vision and graphics and videos and multimedia, but many other topics are related to that. Our speaker today is a professor in École Polytechnique, and she has been previously in many other relevant positions in the UK, in Oxford, and she's having an experience also in Edinburgh and in Grenoble, and in many relevant research groups and places. So I'm sure we all will enjoy of her expertise on this topic. She has been very active at the international level with a high visibility in important conferences with several awards. And then I'm sure that we all will enjoy of the presentation itself. And this is also thanks to AIDA. As you all know, AIDA is doctoral academy that we are going for AI in all its edges, and we try to foster talent, resources, contents, interactions, joint projects, connections to companies. So I encourage you all in the audience to go and see the website of AIDA to find if you have there any relevant course for you, for university, for your colleagues, for your group. I encourage you all to tell other universities to join AIDA. I encourage you all to come to these excellence lectures. Like today, we will have a very interesting one also at the end of February. We try to have 2 per month minimum. So keep tuned for the next conferences coming, and spread the word. Tell your friends, colleagues, and partners in research that we are having here really interesting stuff. And this is the context where we are. We are delighted to have Professor Kalogeiton today, and we will hear her for around 45, 50 minutes. You please, in the audience, feel free to submit your questions to the chat of the meeting. And of course, you are also encouraged to stay at the end and ask in loud voice any questions you might think are relevant and interesting for you to our speaker. So please, Professor Kalogeiton, the floor is yours. We are listening to you. Thank you.
Thank you, Professor Enrique Alba. It's my pleasure to be here. I'm very happy to present in this series. It's very weird to hear myself as Professor Kalogeiton. I would rather go by Vicky, so feel free to call me Vicky, all of you here. And today I'm very happy that I'm going to present to you some of the work that we have been doing in my lab that is around visual generative AI. So one thing is that I know that questions are supposed to be at the end, so I will leave time at the end to have questions. But please, at any time that you have any question, please write it in the chat or just your hand up and put your hand up, and I will. I'm looking at the chat, and hopefully I will be looking at it all the time. So I will answer. So I would like to make more interactive. At some point, I will ask you some questions, but feel free to ask anything. So today I'm gonna discuss a bit, as I said, the work that we have been doing in my lab that is around visual generative AI. And in particular, nowadays, when it comes to deep learning or generative AI and so on, like what we think of when we think of scale, we think of religion. Like we increase the data, we increase the parameters, we increase the compute, and we have better performances. And my talk today aims to challenge exactly that. Is scale all we need? Is what we want to have all the time, like more data and more parameters and more compute in order to reach better performances? Can we have something that's complementary to scale? How can we understand what type of scale we want at every time. So this is the type of work that we have been doing. And as I said, like I'm a professor at École Polytechnique. Most likely, none of you knows this university. So this is a university in France that like people don't know universities in France, which is totally acceptable. So this is a place where people like Poincaré or Poisson or Mons or Lagrange that you have most likely heard from your many math classes either graduated or were here professors or both of them, both of those. And before that, I was in Oxford, as Professor Alba said, and many, many months ago, I did my PhD in Edinburgh and Grenoble at INRIA. And I will not say more about me, but I want to go directly to the topic of today's work. So basically, to build intelligent robots, we need to move beyond what is called like just a perception. So initially, the goal with perception was to enable systems that are able to see the world, imagine and act with intent. So we start with perception. Robots today are very, very good, or basically not only robots, but any type of embodied agent. Either we want it to be automatic cameras or embodiments, or like robotics is the ultimate application, but are very good at tasks like visual recognition or mapping and detection. So this is about mostly answer the question of what is here. However, perception alone is not enough. Next, we need imagination. So given what this embodied agent sees, it must be able to generate this type of plausible and possible futures. So it should be able to reason over uncertainty, it should be able to maintain some beliefs about the environment. And this is quite crucial, actually, when it comes to acting over uncertainty, where we have like this type of generative models that are very good at. And basically here the question becomes is what could be true? And next, we would like these embodiments that not just react, but actually act intentionally. So this means that, oh, there's somebody in the waiting room. Okay, that's fine. So this means that generating motion or behavior that would like to reflect this type of goal-driven generation, or to have like semantic control, or contextual understanding, or intent, and so on. So we would like to have models that ask, what should I do given what I think that the user or the human that I'm collaborating with believes or thinks. And this actually, together these three stages, think, imagining, and acting, form the basis of what we like to say like this efficient generative brains. So underlying them, basically, we would like to have, we have one core need. We want to have minimal data, we want to have efficient compute, and we want to have the ability to model intent and belief. And this is like this type of theory of mind in intelligent agents. And we like to have that for agents that exist in our living room, that are just one chip away. So the question becomes, why does efficiency matter? Why does it matter? So first and foremost is the cost of entry. So cost of entry, like training one of these models, like it's called Stable Diffusion. It's one of these models that is big in text-to-image generation. Back in 2022, cost around 2 million. So actually, this makes the barriers very, very high for academia and several other labs that are not like big sponsored labs. And being able to do research into this type of training is prohibited, which actually is the thing that kind of hinders the next part, which is democratization. So democratization is implied, is more latent, that basically having efficient models allows more people to participate in research. So this is what research should be about. So like we should have it for everybody, and everybody should be able to enjoy for it. To enjoy it and to be able to progress. And democratizing this type of generative models is very important if we want to have like more true progress, instead of having all the power in hands of like these big companies. And we should have these production models, but we should also be able to have like more things at the institution level, excuse me. And the other part refers to data efficiency. So for instance, when it comes to other fields like medical data or satellite data, or any other type of data that we want, or even if we want to create, I don't know, our own set of purses, then we don't have billions of images. We have a handful of data every time. So we need to be able to understand what matters every time in data and how can we do more with less. So what are the challenges that efficiency faces? So these are the things that I will, part of them that I will discuss today. So first is the training data. So this is actually easy to understand that efficiency in training data means that collecting the data, filtering the data needs to be by itself is a process that is enormous. And we all know about the big models and LLMs that they are fed with the web and you download everything that exists and so on. So this actually makes it very, very big. And there is, again, a hidden type of challenge that is privacy and copyright and all these things that somehow nowadays is considered okay, that everything is online, we can use and that we can train on. However, it's not necessarily the case. The second part refers to model, where for model, we mostly refer to the model size, which means parameters. The more the parameters, the larger the model size. And the other thing is the resolution. So the resolution is the output of the model. So when it comes to generation, or when it comes to temporal consistency, temporal window in information, and so on. Another part is the training and the condition. The question becomes like, how can we condition and how can we avoid these long-term training times that actually imply a lot of compute? And then the last bit is that given that we have these models that are great and that they have very, very well in labs or even in companies and so on, if we want to actually use them in real time and to deploy them in our homes or in our labs and so on, what we need to do is to adapt them. So this adaptation, either from continuum learning perspective or from fine-tuning perspective, this is like how to deploy them at inference time. So how to make this post-training efficient when it comes to really deploying things that they need to run very fast and they need to run on a chip. So as probably you all know by now, there exist mostly two very famous type of generative AI architectures. The first one is transformers that are very used to model kind of sequential data. For example, text and code is great right now. If you want to create a startup, it's now the time for these things or any type of time series data and so on. And the examples, this is Claude or Llama or the GPT series and so on. So this is great. And then the second category are the diffusion models that are great for continuous data, for image data, for video data, where spatial resolution matters, or audio. Examples of these are stable diffusion, or DALE models, and so on and so forth. So today, I'm going to focus on the second category of models without loss of generality. And just for those of you that do not know what diffusion models are. So diffusion models is this category of generative models where we start from an initial sample, for instance, an image, this X0, and we sequentially add noise, that this noise follows is a Gaussian noise, until the final step, where in the final step we end in a full Gaussian noise. So this is the T capital step, resulting, yielding this XT final sample. And this process is called the noising process. And respectively, what we want to do is to denoise it, which means that we start from this random noise that we can actually get with a random Gaussian noise with a random generator in our computers. And then we would like to sequentially, slowly remove the noise such that we end up in the initial image. And to do that, it suffices that we train a network that is with this parameters theta that is learning the noise that was added at training time at every step. And how do we do that? We know that basically when here we are adding Gaussian noise, and this process is Gaussian. And to remove Gaussian noise, this red thing here is also Gaussian, which means that it has a mu and a sigma. So these are the two properties of this Gaussian distribution. So at generation time, what we are doing is that we are trying to create a network that has this mu and this that predicts this mean and this variance that match exactly the ones of the denoising process. This is at a very high level. And the results have been great. So here we see some examples from DALE 2, that is from the company OpenAI, that is I guess you all know, mother company of ChatGPT, that we have like examples, like for instance, an astronaut riding a horse in a photorealistic style. So we see that was already like 4 years ago, back in 2022, or these teddy bears mixing sparkling chemicals as mad scientists, that we can have like this very beautiful images with a lot of details, and this kept going. For instance, then we get the DALE 3, that this is basically the model that exists within ChatGPT. If you type today, generate an image of a pink elephant, that's the model that's gonna, like on ChatGPT, that's gonna call. Midjourney is the one that is the most the model that you paid. It's the closed source, that paid model that usually beats all the benchmarks when it comes to generation, because you can have a lot of controllability in the prompt. And there exists the open source counterparts, for instance, Stable Diffusion or Flux and so on, that produce very, very well images, are usually a bit below the counterparts, parts like the ones that are closed source, but still excellent in quality. And of course, this thing also applies to video. So for instance, here we can see examples from text-to-image generation from back in 2024, 2 years ago now, from Sora, which is the text-to-video generation from OpenAI. And we can also have like the same thing can apply also to other fields like motion. Motion is the thing that you want, like it's a human, usually refers to human motion in 4D space. So we are trying to model the various coordinates of the human in space and time and how they move. It's like the avatar, so that's what Meta, like initially they were planning to do with the metaverse, and so on. So I wanted to show that basically diffusion models can be applied to several different fields and have been the default architecture. And basically, this type of models show also one more thing, that they need a lot of data, they need a lot of parameters, and they need a lot of compute. And as I said, what I want to address with my work is that, do you really need all these? So as I said, like I will start with these 4 different challenges, and I will mention like today 3 of them for the sake of time, and I would be happy to also discuss afterwards more if you want. So I will start first with the model. So the idea is actually very simple. Can we have models that require like less, that have like fewer parameters for higher resolution or the same resolution? So this is the answer, the question that we are trying to answer with our work of last year with my PhD students and collaborators here in France, that was published at last year's CVPR. And the motivation is as follows. All models, diffusion models or transformers and so on, are trained by fed with the web, which means that we go online, we scrap the web, and we are getting pairs. What does it mean in pairs? That we get images and then the corresponding text. So the corresponding text sometimes is useful, sometimes it's not useful, especially when it comes to, I don't know, like Instagram or Flickr or whatever other you youngsters put, like hashtag Mojito or anything else that exists out there. And basically, when we train with noise, training becomes much harder. Therefore, the default step is called filtering. What does it mean filtering? For every image that we want to generate, that we want to reconstruct, and the condition. So let's say that here the condition is text. I know the examples I'm going to use is text, but none of my works is limited to text in this. And we have also other conditions as example in the corresponding papers. We would like to measure the coherence between this text and the image. When the coherence is high, then we consider this pair as good. And when the coherence is low, because it's not informative somehow, the text for that particular image, then we discard the pair. So basically what happens is that we discard something around 90% of data. Instead, what we are saying is that since we have downloaded the data and since we have had this measurement between the image and the text and we have measured this coherence, let's use this and let's give this coherence score to the model itself, to this generator itself, and see what it's going to learn how to do. And our finding is that when we provide the model with this coherence score, it learns what to do with the conditioning in presence of low coherence scores. So the model learns to act as unconditional when the coherence is low, therefore not taking into account the condition, as class conditional or context conditional when the coherence is very high. So for this, we also train our own diffusion model, which is relatively small. So I will not go into details, but let me show you at a high level how it works. So we have here our condition, that is the text that is tokenized. And then here we have the coherence. Then it goes through a series of self-attentions. Then here we have some latents that are the ones that are able basically flexibly to assign different type of compute at different types of pixels. So here we have the pixels. So here we have cross-attention between the condition to the latents. And here we have cross-attention between from pixels to latents. So we are attending the latents. Then we have a series of blocks of self-attention. And then we can have, again, cross-attention from latents to pixels so that we generate finally our pixels. So we are basically splitting the computation into the condition here, the image that we want to reconstruct here, that we want to learn. And here we have the latents that give this flexibility to the model. Important thing in this case, so this is, we call it CAD as coherent aware diffusion. The important thing in this is the fact that this type of models can be trained with much, much fewer parameters. In practice, compared to the models at the time, like Stable Diffusion 1.5 or Excel or Flax, ours required 18 million parameters as opposed to the more than 1 billion parameters that the other models required. The training set and all the protocol is released, and the parameters, as you see, is, sorry, this is the training set size, and the parameters is, it makes more sense, is 330 or 500, depends on the version of the model, million parameters as opposed to the billions of parameters that other models have. And when we look at the results, we can have these very nice images as you see here. So let's first see when it comes to coherence. So at this time, we can actually prompt the model with a different coherence, and it's going to give us a different output. For instance, an armchair, given a prompt, an armchair in the shape of an avocado, when our coherence is 1, we will have an image that looks like the one that we want, like this armchair in the shape of an avocado. However, then when the coherence is very low, like 0, then the model is going to be like, it's going to take into account a weak version of the text, because the text is going to still leak some information in the model. So it will still understand that somehow interior space and so on, but it's not going to pay so much attention to into the text. Therefore, it's not going to generate this avocado chair. And when it comes to like comparing qualitative samples, we can see that we can have this type of very high level details, very low level details, very good text adherence, very like photorealistic images. So we can see here the wrinkles or this facial expressions or the texture, and we can also see, I don't know, like this cosmic maelstrom nebula. So we can really think that like we are dreaming here and so on. To conclude this part, we want to say that don't drop your samples, but instead evaluate the condition coherence and condition the network with it. And this results in a model that can behave as conditional and unconditional. And as a bonus, we also saw that we can train our own diffusion model, unlike like mostly like doing training, like using trained models and only doing inference or fine-tuning or post-training or so on, or LoRa's or anything else that you want. And this concludes this part of the work. And yet what we observe is that even with or without filtering, training still relies on billions of data. So even with the filtering, so without filtering, we have a lot of data. But the default paradigm with filtering, that means we remove 90% of the data, has still like billions of data. And then the question that we're asking is that, do we really need all this data? In fact, there is a common trend that says that the larger the dataset size, the higher the performance. So when I tell you that, you'll say, yeah, big group, everybody knows that. So let's see what it means quantitatively. So here we see in the x-axis, the training dataset size in log scale. So here we have like millions to billions of data. And here we have on the y-axis, generation performance, the higher the better. So this is a Geneva score for those of you that are more technical, and the other one is the DPG score. So anyway, like one of the best ways to measure right now generative performance. And the size of the bubbles reflect the model size. So the larger the bubble, the more the parameters, which means that the larger the model. So we see two trends. First trend is that the higher the dataset size, the larger the dataset size, the better the performance. So that's what we see here in this axis. And then we also see that in order to have like a better performance, models also increase in size. And the question that we are asking is that, do we really exploit training data? And particularly, in order to ask this question, we are asking this: how far can we go with a data set like ImageNet that has 1.2 million images only for text-image generation? And the answer to this question is actually pretty far. So if you see here, we train diffusion models with like 1 million images, 1.2 million images that are actually comparable. We have performance on par or even better sometimes compared to like all the other models, the counterparts, their counterparts models, with using like less than 1,000 times less data. And this actually is a work of, it's an ongoing work of my other PhD students and collaborators here in France. And this brings me to the second challenge that I'm going to discuss today, which is really around training data. Let's see how we do that. So this dataset, as I said, ImageNet, for those of you that you do not know, is a class conditional dataset, which means that for every image, there is a class, like for instance, tablets and king penguin or golden retrieval and so on. We do two types of augmentations. The first augmentation is really at the image level, and we do the simple thing like copy paste. So we take images and we copy paste one on top of the other at different scales. So we try like 4 different scales, 5 I think in the paper, as the ones that you see here, and we place one image on top of the other. That's first augmentation. Second augmentation is text augmentation, which means that instead of using the text as an image of, and then we have like an image of a trombone and a king penguin, we are passing this image, either the initial image or this composed image with a copy paste, through a VLM, and then gives us like a caption. For instance, on the left side, the person is trying to interpret, and then on the right side. So we see that this type of VLM is able to actually understand this compositionality, to give us this information about the spatial configuration of what we see, and also understand this level, these details in scale, like this is small, this is high, this is low, and so on. And then we are training a standard diffusion model. In this case, the DDPM model, for those of you that know that actually related diffusion. And the only thing that we change is that we are when we are inputting the data, is that instead of inputting all data at the same time, we start by giving the model like first the easy samples, which means first images that don't have any augmentation, and then slowly we start giving these cut mix images where we have these copy pasted parts. And then we are just learning the model as you have seen in your standard like diffusion models. And then we examine the results. So quantitative analysis of the results shows that what type of augmentations and how they help. So we see that we also try like prop augmentations, if you want to discuss afterwards. And in this case, we see that actually we can have much better augmentations when we add much better results when we add the image augmentations. And then we are evaluating our results qualitatively. So here we see the output of a model that is trained only with a text saying an image of, like just an image of that. That's how the model is trained. But then at test time, we can prompt it, like for instance, a teapot and cookies on the table. So it's like very bad. When we start adding text augmentation, we start having some better results. For example, a teapot and cookies on the table, then we can have something much better. And by adding also text augmentation and image augmentation, then we end up into something much better. And when we compare actually qualitatively results compared to the state of the art or one of the state of the art open source models, then we can see that we have very good results. And for instance, the ones that you see here, like a bird and its reflection on a fountain, that we can really see a very good reflection, or the old man that we can have like this again, wrinkles, a very nice talent, like a very green eyes and so on. As opposed to like this that, I don't know, makes the bird green, etc. And then we are asking, what about resolution? So can we have models of high resolution, which means like larger size? And the answer is yes. So the images that you saw before were actually generated with 256 resolution. And to do 512, what we do is that we do an extra 50K of fine-tuning steps at high resolution. That's all. And we see here that the performance increases. Again, like the various results in here is overall performance. And which actually begs the question, is it all about initialization? So if we find a very good initialization, can we always get more performance? But anyway, and here we can see some actual qualitative results that we see that in this case, note that the images are the text encoder is not changed at all. But what we are doing is that we are only adjusting this image tokenizer, and we have this very beautiful images and very photorealistic and that you could really imagine seeing somewhere on Twitter or Instagram and so on. And when we compare to the state of the art, we see that we are actually very comparable and sometimes in favor as opposed to the state of the art, despite of the fact that we use only 1.2 million data. So if you see here, other models use 5 billion or 1 billion or 25 million, that's the smallest one that we outperform. And in all cases, then you see that we are either comparable or second best or something like that. And on average, besides this model that has 12 billion parameters, and we don't know about the training data, in all other cases, we are very comparable to these open source models, which actually begs the conclusion or the question or whatever it is, that actually scaling training data, scaling the parameters is not required. We can have the same results with 1,000 times reduction in data and 100 times reduction in parameters, like times 3 and times 2, which is contrary to popular belief. And then we're asking the question, what about aesthetics? Can we have something of a very high aesthetics? So the answer is yes. So in this case, we fine-tune on our model on a small data set of 400K images, and we adjust the tokenization so that it can handle this larger input size. Because we are also upscaling to 1024. And here we see again the results compared to the state of the art at this resolution. And we see again that our results are like comparable. Again, we have so much fewer data compared to the billions of data, and our results are on par to the state of the art, the real state of the art. And so here, if I ask this question, so we have, for instance, a fox with glasses and dressed in white shirt and high cargo. And we would like to assign models. So I'm telling you that this is Stable Diffusion and this is PixArt Alpha. And if I ask you which one is our model and which one is Stable Diffusion 3, the medium model, who can guess? This image, do you think that this is ours or this is from another, a big commercial model and so on? Can anybody guess? I mean, if we were face to face, I would force you to actually do something with your hands, or I would pose a lot. So it's okay if maybe just ponder yourself for a minute. The point is to show you that we cannot easily differentiate. So the ones that have amongst you that have already played a lot with generative models perhaps can have a better clue. However, the ones that have not seen that, then we can really see that everything is quite comparable. And this also stands for several other images that these are not cherry-picked, like plants, flowers, trees, big things in the wall. We cannot really tell which one is which. So if I ask you which one is ours, I don't know if you will be able to say. So in this case, ours is the last one. And the point is that this is comparable to models with in terms of visual quality and high aesthetics and so on with already existing models. And then we want to answer two questions. What about compositionality? Compositionality is one of the most interesting things because it actually somehow, at least in my opinion, signifies this type of emergent properties of emergent reasoning of generative models that are able to understand the configuration and reason about the physical world. So we can see here that the model is able to do this composition that when we are asking for this teddy bear with glasses, then the glasses are being placed exactly at the point, even though this is really out of distribution compared to the training set, is able to do a pink elephant, even if it has never seen pink elephants, or to do oil painting or other types of paintings that for you, of course, it means nothing. But however, for this type of models, this is quite hard because it has never seen this type of data. It's really out of distribution. And when it comes to generalization, we want to see the capacity of the model to generate concepts that it has never seen before. So we are asking it to generate, for instance, an iPad Pro rests on a rustic wooden table. The tablet is positioned at a slight angle. So this is the data set collected 20 years ago. So iPad didn't exist at that time. Hence, it being able to understand how an iPad should look like. This means that the text leaks this type of information and is able to generalize to this type of fancy concepts, which is very good in my opinion. So to conclude, with this work, we want to show that data is enough, and we can go from billion scale datasets to 1 million datasets with augmentations. And we can reach the performance on par to model models while training only with 10 times less parameters and approximately 1,000 times fewer data. And I believe that this actually opens the gate towards a more accessible and AI that can be a type of step that is a step towards democratization, that an entry point that many more people could participate in this type of research. Okay, so we'll move to the last part of what I'm going to present today, which is again based on my initial slide, that we can have as I said, the standard paradigm is collect billions of data, filter and discard. Good, we have seen that. In practice, what happens nowadays is that this is not enough. This you have seen also with ChatGPT and so on. What happens is that after that, this filter data set goes through a diffusion model, and the results are not there. But instead we have this additional step that is called usually the RLHF part, which is aligning with human preferences. What does it mean is that we want a model to be able to give us something based on the preference of a human, for instance, high aesthetic or with physical awareness, or like to make it more in the style of a particular painter and so on. And we do that usually with this type of loop, that this is an RL loop. However, I will argue here that this actually, first, we discard informative low quality data. So if we discard this, we're as I said in the first part, we are discarding the models. Having these two type of objectives complicates training, because here we have one objective, and here actually this thing is an additional optimization step that in the paper we saw how these two are contradicting each other, because we are first learning I can actually describe this at a high, like the insight is quite elegant, that we have like this nice distribution. And with a reward model, what we're trying to do is that we try to find peaks into this distribution. So we're trying to make our model, instead of learning this generic distribution that has learned the nice manifold in this latent space, to actually go to one particular place. And this is then against the initial training of the diffuser model. Also, this is very, very, very prone to overfitting to a single reward. This is called the reward hacking. What is a reward? For instance, I want my image to have high aesthetics, or I want my image to look like a style of some particular painter. So this is a reward that this is an external model that gives a particular score. And one of the main issues with this type of architectures, this type of post-training, is that reward hacking, it means that we will have we can make it overfit to this particular model, which means that we don't necessarily learn a good distribution, but we're just overfitting to that, which in turn harms diversity, which is also known as mode collapse, or the semantic fidelity and efficiency of the model. And instead, what we are saying is that rather than actually correcting a pre-trained text-to-image model, can we teach the model how to trade off not only one, but multiple rewards from the beginning? And this brings me to the last part that I'm going to discuss with you today, is around training and conditioning. So this is, again, ongoing work of my PhD students and the collaborators here in France. And basically, here we see the pipeline that I will briefly discuss with you, the training pipeline. We have our initial image, and like for instance, the caption is volcano. And this we score with external models. So every external model can be like a clip, for instance, how much the coherence between text and image, or it can be like pick a score or any other model that exists. You go to Hugging Face, you download from the suite of reward models, and you score it. Great. And you have the scores. And then what you can do is add this as additional condition to the model. So here you have the standard training objective, but in this case, not diffusion, it's flow matching. It's approximately the same thing. And you can have your initial image, your caption, and also this score as a vector. And you can condition this model on this vector. And then you can have your final image. And then at test time, so here is what we see with inference time, what we can be having is that we have like what we want the image, and then we can have the highest score. We just max the score, we minimize the score, and then we do a classifier guidance between the two. So we take the difference between the two, and then we have the final guided image. So this is more technical. If you do not get exactly that doesn't particularly matter. However, by doing this type of, the important thing in this case is that we are giving this type of information, this type of reward to the model to begin with. So instead of giving it as done here, with an external model, so we first train and then we change essentially the weight of our model, we give this information directly here as an additional input to our model. So this is the important thing here. In this case, we vectorize it and we bin it, and there are many details to discuss there, but that's the important part. And when it comes to results, we can see that it's able to create like very, very good images. So first we start with qualitative results, very nice volcano, very nice faces. It's even able to like have text written on the images and have a lot of details and things that are photorealistic, things that are imaginative, things that are futuristic, and so on. And when we want to examine parts of the model, then first let's start. I will show you like 4 different properties, but there are several more described in the paper. That the first of all is that it outperforms single reward approaches in all metrics. So here we see with orange we have a model trained with all rewards, and then each other color refers to models trained with 1 reward. So let's just zoom in into one of them. So for instance, in this case, ours vs only a model trained with one reward, first of all, we see that in that particular reward, that other model performs best. But in all other things that we are examining, so these are different metrics, our model has a best accuracy. And also here we see one thing. This is called reward hacking. We are training a model for that thing. And in that thing, it performs very well, great. But then it's actually, the performance in all other metrics gets disastrous. So this is the second part, which is called mitigate reward hacking. Another thing that I want to discuss about is that it significantly, that our model, it significantly improves training. So for instance, here, based on various rewards, then we are examining basically the training step, and we see that with our model, we can reach the same type of performance, but sometimes 20 times faster, sometimes 3 times faster, but in all types of cases, it's significantly faster, which actually shows that it accelerates training convergence. And we see the same thing qualitatively here. So for instance, here we see the baseline model, how it produces this, tiger with a tuxedo, a tiger wearing a tuxedo. Whereas in this case, our model, much faster while training, is able to produce something that follows this text and at the same time produces very good photorealistic results. And is very good in all types of metrics. Another nice example that I like showing is this: a panda mad scientist making sparkling chemicals, because very early in the training we can have something that is doesn't have when I here, when I there, that looks like a Casper the Ghost or something like that. Then last property that I want to discuss is that it outperforms synthetic captions alone. So so this is actually an essential point for me, because most modern models right now, what we have been doing is that they are trained with captions, with static captions. So let's see what we have here. The gray performances is the baseline that has only real captions. Great. And then we have our baseline. This is the orange one, when it is trained only with real captions. And then we have synthetic baseline, which means that we have synthetic captions that on top of the baseline, on top of the standard way of training a diffusion model. So this is the purple. Sorry, this is the blue. And we see actually that in some cases, in most of the cases, the orange itself outperforms the blue. So here it outperforms, here it performs on par, here it outperforms, here it's a bit less. But which actually is quite important by itself, because it shows that having this type of conditioning early on makes the two objectives merge much better, which results in naturally better performances that we don't need to counterbalance by having a lot of synthetic captions that are big and long, and you need to ask a lot of VLMs and so on. And when we combine, of course, our method with synthetic captions, then we improve significantly overall performance. And we chose that actually recaptioning by itself can also benefit our model. And here I want to show also the fact that we can have this reward controllability. So if we, in our case, that we optimize for all types of rewards, we can have this type of graffiti on the rocker chip, on brick wall, vibrant, high contrast, neon, pop arts, colors, so on. And if we optimize for each one of the rewards, then we will have images that look very good in a particular reward. For instance, image reward or clip that it aligns with text, or a pic score that or size score that examines the physical plausibility of an image, and so on. However, combining them all together results in something that is also visually much better. And here we saw also the evolution of the reward. So here we have the aesthetic score, and here we have the image reward over time for each of the words, over each of these frames. So we see how it evolves, how they evolve over time, and how that they both align quite well. And the last for this is that in all scores, as happens with most generative models, we can do test time scaling, which means that we can run a lot of best of n in this case, and we can actually get much better performances with our model as opposed to the baseline, as you see here, and much faster. All right, to conclude, we condition on a vector of rewards to integrate alignment to training, which actually outperforms non-conditioning or single reward baselines, converges faster, and mitigates reward hacking. I didn't show this at all because, okay, like these are big tables. However, we outperform the state of the art in all types of things. I have actually the slide. So here, if you want to to see, this is I have several of them. So this is a part where we outperform. So this is the state of the art, and here we have ours. So we see that we outperform the state of the art in overall score. So for instance, for 67, we go to 68. It's this. Oh, this one. Anyway, I didn't show this at all because, okay, this is just a big table, not just like a big table of numbers that. But I can just tell you that. And for future, we want to, of course, combine it by training it on ImageNet, so to see how we can leverage fewer data, and perhaps have more personalized rewards that we can have it like as a function of personal styles and adjust to what everybody would prefer. And this concludes this part of efficiency, where I discussed training data and model and conditioning. And then the question becomes, when it comes to the future, so what will I consider as something very important? So one big area right now that is booming is around humans, that is multimodal and human object interaction and human-human interaction. This is very big, and this when it comes to generating humans in space and time in this for the humans. And another thing is this robots that we have, like visual SLAM and robot learning and manipulation, that not only from the hardware perspective, but also from the visual SLAM perspective and from the algorithm perspective. And nowadays there is this big field that is becoming a field that's becoming bigger and bigger, that's referred to as spatial AI, that we refer to things that are physical aware agents like humans that they operate in this type of 3D environments, as robots should be able to do, and physical AI and so on. And this is has given birth to several ideas and startups, and it's all over the news if you Google it nowadays. And in my opinion, one of the things there refers to really efficient human-robot collaboration when it comes to the spatial AI, where in particular, for me, things that we should really pay more attention to refers to representations, or how to abstract data, or how to have more reasoning, and so on. And what I think is that we can go from perception to imagination to collaboration, but more efficiently towards more this human-machine collaboration, and of course towards this holy grail, this greater goal of all these different fields being merged together. So thank you, and thank you also to my PhD students. Thank you for your attention. And I'm very happy to take questions.
Thank you. That was great. Thanks a lot. Very interesting stuff you have there. Thanks a lot. So yes, we are now in the time of questions. We are having one question there in the chat about the experiments, and then we have a question about, does Miro versus Synth Miro have the same amount of parameters as the number of iterations on the training data?
Yes.
Or because you're introducing more data, the system is being trained 2 times with the same baseline. So I think this is going on the fairness of comparisons.
Yes. It's a very good question. We made sure that baseline and Miro have exactly the same parameters. So baseline is always trained with 1 reward, but the same number of parameters, same number of data being seen, as opposed to this. The difference in time is that to compute more rewards for Miro, it requires more time. That these are external reward models that we score basically for every image. But the model itself, compared to the baseline, everything exactly the same. But it's a very good point, actually, that you are asking.
Okay, thanks for your answer. If any of you in the audience are having more questions, please write in the chat or raise your hand and you can talk to our speaker. In the meantime, I have a question about how much the person, the researcher of human preferences are playing a role here. Are you taking into account, because there's the aesthetic measure, and at the end images and videos are to be consumed by persons. So how much are you controlling in a scientific way the opinion of people about the results and putting them into the training or the evaluation of the quality
Yeah.
of the results?
Yeah, that's actually, yeah. Thank you for the question. That's like a reviewer too. So basically, when people train like among generators, what they care about is aesthetics. So we want something to have a high, very something visually pleasing. So this usually is one of the first criteria, and which has been one of these our driving force in order to have this very visually pleasing images. Of course, compared to models trained at industry that they have many more parameters and also many more parameters and many more training data, some parts are not at the level of this type of models, but some of the other parts are. So aesthetics is one of the important things, and the aesthetics somehow this is subtle because most people prefer high saturated images. So most users like colors that are very dominant, like this red that is sparkling, and the yellow with big contrasts in edges and so on. And with this, we can actually tune at test time. So it's one of the good things. We have actually online the demo that you can tune at test time. So you can have this personalized preference, but it will not be necessarily the default thing of a model because it does not necessarily align with natural images.
Okay. Thanks a lot for your answer. We have a question from the audience, Itamar Halevi, please.
Yeah, I have two questions or two comments. You said you want to minimize the data, and you demonstrated that you do it successfully. But how do I know the proportion of parameters, number of parameters that will be also reduced?
Yeah, that's so. You're right. You're right to ask that. And basically, parameters and data are not decoupled. Indeed, if you have a model that has few parameters but a lot of data, you will overfit. And if you have not enough data and you have too many parameters, then you will undertrain. You will be overparameterized. Indeed, these two need to be in accordance. However, for diffusion, there is no today. There is no rule for LLMs this exist on how what is exactly the correlation and optimal correlation between number of parameters and number of training data. So people keep increasing them both based on the compute, and this results in something better. In our case, what we did is that we chose as training data the ImageNet training data. In this case, we add this thing that we fine tune. And for parameters, we chose something that is small enough for us to train with less than 1,000 H100 hours because we're an academic lab and we need to train it. But indeed, having more parameters could help with the model. In this case, it's not really needed because, as you see, it's actually the very, very low scale of parameters. It's comparable to models that existed like 2-3 years ago.
So this is like specific example design decision, right?
Yes. But
okay.
it's
I want to go to another point.
Yes.
At the very beginning, you talked about robots and also towards the end. And you used the word perception, imagination. And at some point, somebody asked me to define science or mathematics. So I said imagination and intuition. Now, how do we assign to our robots these two elements which are kind of touching the creative border of our endeavor? And then how we, even if we are successful, how we differentiate between the engineering imagination intuition versus the scientific one.
It's a great philosophical question that to discuss over a cup of tea and coffee as a more thing, but it's actually very interesting. So if I'm able to answer like to the point, how can we have like these embodiments in a way that have intuition in addition to imagination? I do not know. I hope that we will get there by having more and more understanding in how they work. Humans, we have intuition by having this type of social intelligence, by interpreting very, very social cues. My assumption is that if we have embodiments that are able to understand humans' behavior at the social context, then these ones will be able to have more insights about particular choices or actions of a particular human. And imagination goes hand by hand with this, because imagining what the other person will do and then doing it as a feedback to verify on oneself. But that's at a very specific level, and then the rest, I guess, it's like over beer or something like that, because it's very philosophical and
That's
generic.
interesting. Indeed, we have 3 questions in the chat, but I would ask for you, Vicky, to go fast in the answer, please.
Okay.
So
models available on GitHub. Yes, that I saw.
Yes.
Everything is on GitHub. Everything is online. Code is there.
Okay, this is great. And then Mathieu is asking about the actual meaning of a scale if you are needing previously trained models and they are the scale and they represent the big scale.
So overall, your models work better with less data because their quality is improved by using pre-trained MLLM or equivalent, which is the reverse of current trend. That's interesting. For me, this raises 2 questions. One, do you need pre-trained models with huge number of data? So scale is needed at some point. I can answer this directly with a graph. Is this the graph? No, that's the graph for the last bit. So I can tell you directly that when people think that this MLLM that gives the captioning is having so much data, it is not the case because it's trained with 200K images. So instead of 1.2 million, we go to 1.4. Unfortunately, I don't have this this slide here, but so it is not the case. 2, quality seems to compensate scale. Sorry. Quality seems to compensate scale. That's great, but if quality doesn't scale, which seems to be underlying your results, what is the next step to improve the performance? Compensate scale. All right, so compensate scale. What I want to show is that not that we should not scale. That's actually good that you're mentioning it. My message is that scale, but think first. Think what you need to scale and how to scale. So in my opinion, we should scale, but we should scale smart. Just adding more data without including diversity or without examining what type of data we need and how to train the models and how to condition them, sure, it's going to improve performance, but that's not necessarily the only way to scale. We can think first and then scale smart. So that's the short answer.
Okay. We have another question there regarding the multi-reward system.
Yes. Could you please elaborate a bit more on how each reward is targeting specifically its dimension? Okay. Do you have specific metrics that measure its dimension dependently? What is it you want to apply a reward that is more complex and with indirect ways to be measured? Any insights on this? Yes, on dimensions. That's okay. So reward models are external models, godlike models that are trained by somebody is actually big research teams that they go online, they select a lot of data, they ask various evaluations, and they are able to give a score for every particular image. A very classical reward model that perhaps all of you know is called CLIP, that basically measures the alignment between text and the image. So how well the two are aligned. And the CLIP is used as a reward model in order to bring the generated image closer to the text prompt as input. Other types of reward models are models that have high aesthetics, or they have physical plausibility, or they have particular other types of scores. So and how it's being measured, yeah, this is so it's very also good that Sorry. All right, so here we have a lot of evaluations. The main evaluation is GenEval, where this is a benchmark that we are measuring several things. For instance, single object, how well the final result is on single objects, on two objects, on positioning, on counting, on color attribution, like the rank, red, I don't know, beard and the blue suit and so on, like this. That's one category. Another category are these party prompts that really refer to these particular rewards like HPS or image reward or aesthetic quality or pick a score, as they are called, that we measure those particular attributes of that particular image that these are directly scores. If this answers very fast the question. Okay, thanks. I got the answer. And the link or a keyword? What is this question?
This is for probably locating your work in GitHub or.
Yes. So the easiest way is to go to my website and check each one of the papers. So each one of the papers has a project page, and the project page points you to the particular code and GitHub, either to my website to find the papers, or to the paper titles if you remember them.
Okay. So the keyword is your name.
Them.
The keyword is your name and your website, and from there they can take it. Okay.
Yes, exactly.
Thanks a lot. That was wonderful. We answered all the questions. They were very interesting. The contents were amazing. Thanks a lot for that, Vicky. Thanks a lot to our audience to be here. I encourage you all to attend the next excellence lecture at the end of February. And we finish here today. Thanks you all, and bye-bye. Thanks.
Thank you. Have a nice evening.
Nice evening for you all. Bye-bye.
Bye-bye. Bye-bye.